Hello everyone, am I audible to all of you?
Yes, sir, audible.
Okay,
Yes, sir.
so let me start and we'll end the syllabus today. So last class we have discussed about what is static timing analysis, followed by the definition of setup and hold time. Then what do you mean by setup violation and hold violation? Taking a standard diagram into consideration where there are two flip-flops and in between there is a combinational logic block. And this circuit we are describing is a synchronous circuit. So we saw what is the difference between propagation delay of combinational design followed by the propagation delay of sequential design. Okay. So here, what we have seen is uh, though the input is changing much before the clock, the output will be changed whenever there is a positive edge of clock happens. Okay, so as this is a positive edge triggered clock, so that's why the PPLH, the propagation delay, where output is traveling from output value is changing from low to high, is TPLH is with respect to 50% of the clock and 50% of the output. Okay, in combinational design, it is 50% between input and output. Okay, so that is the basic difference between your propagation delay of combinational design and sequential design. Okay, so so depending upon the setup time and hold time, it also helps you to find out the maximum clock frequency of a circuit. Okay, so now we have taken few examples where we have to find out the maximum clock frequency of a circuit. Okay, so in this, while you are defining or you are finding out the maximum clock frequency of the circuit, here combinational delay plays an important role because you will find combinational delays are the actual computational block or functional unit block which is doing the actual computation. Registers are there for storing purpose. Okay, and so hence combinational block we cannot avoid. It will be there mandatorily in between two flops. Okay, so people sometimes to flip-flops they used to call as flops only. So so combinational logic block play or the delay propagation delay due to combinational block plays a very important role while deciding the maximum clock frequency of a circuit. Okay, so we have taken one figure here, and in this same figure this is synchronous based synchronous clock. Two flip-flops are getting clock at the same time. Then you can see flip-flop 1 has a delay of TCLKQ. So from CLK to Q, the flip-flop propagation delay is 10 nanosecond. And then the input at D will appear at X. Then the X will be inverted. So here the minimum combinational block we have taken an inverter. So X will be inverted with a propagation delay of 5 nanosecond and it will reach next to Y. Okay. Then after Y there is another flip flop which has again clock to Q delay as 10 nanosecond propagation delay of the flip flop 2, and the setup time is 2 nanosecond and hold time is also 2 nanosecond. Okay. Okay, so this is the question, and we have to find out what is the frequency of operation. Okay, so and we have to see what is the importance of setup time while deciding the frequency of operation. Right. So let us assume the data is already present at the D input of the flip-flop 1, or you can say flip-flop A, and it is in stable form. So we are not considering the setup time of the flip-flop A. Now the clock pin of flip-flop A, that is clock has been triggered with a positive edge of your clock pulse. So clock is traveling from low to high at 0 nanosecond. As the propagation delay of sequential circuit is TCLKQ, it will take at least 10 nanoseconds so that a valid output will be available at the X, okay, which is the output of the flip-flop. Now, the data when it is launched due to propagation delay of the flip-flop A, it took 10 nanoseconds to reach at X output of the flip-flop. Then after that, it encounters the combinational logic delay. TPD is equal to 5 nanosecond. And now the total delay occur is 10 plus 5 nanosecond is equal to 50 nanosecond. Okay, so note it that we are trying to find out the maximum clock frequency of a circuit. So that indicates that you can see here maximum clock frequency is equal to 1 of minimum clock period. Okay, so whatever minimum clock period required in which the operation can be completed in a single cycle, so that clock period we have to find out. Okay, then we have to invert it in order to get the maximum clock frequency of this design, right? So it's a very simple question. You know how to do and to find out the clock frequency. But why we are discussing, we have to see the importance of TS. That is your setup time. Okay, so you have to also consider the setup time in the flip-flop B. Okay, so there are two flip-flops, and in between there is a combinational circuit. And in more complex design, in reality, you will find in a single path there will be many combinational design. Okay, so whatever combinational design are there in between X and Y, so all the delays, if it is there, you have to add it up. You have to sum all the propagation delay. After that, you will get the final delay from clock till Y. Okay, so once it is done, you know that the data must reach at the flip-flop B in order to store or latch at the flip-flop B. So data must reach before setup time, before TS time of the clock triggering. Okay, that you know. So that's why. So what we have to do is we are finding out the clock. So we have reached at Y, and if the delay is 15 nanosecond, so we have to add with 15 nanosecond another delay that is called as setup time of the second flip-flop B. Okay, so now between two consecutive positive edge of the clock, the delay is 10 nanosecond plus 5 nanosecond plus 2 nanosecond, that is equal to 17 nanosecond. Okay, so we can say that for this circuit, the minimum clock period should be 117 nanosecond. In order to it will operate in a single clock cycle. Okay, so now you need to finalize, or in order to generalize a concept or a formula, the minimum clock period is equal to, in this type of circuit, TCLK Q A to Q, TCLK Q of A, then TPD of F plus TS of B. Okay, so now in this case it is 17 nanoseconds, so you divide it by 1, so minimum clock period, and when you are dividing it by 1, whatever value you will get, that will be the maximum clock frequency of this circuit. That is to say that all the entire circuit operation can possible if you are taking the maximum clock frequency as 1 by 17 nanosecond. Okay, and here you know how to find out, it's not that important, but you always remember when you are approaching the second flip-flop. So we know the data must be stable, or it must reach the second flip-flop before the setup time of the clock triggering. Okay, or clock edge happens. Okay, so that's why after 10 plus 5 nanosecond, we are adding the setup time of the second flip-flop, and then we are deciding the entire minimum time duration, then finally we are deciding the maximum clock frequency. Okay, so this is one type of approach where you will feel what is the importance of a setup time, right? So we'll go to another example. I think it is you can understand it well. So there will be no much doubt. So let us see another example where there are more flip-flops. So in this circuit, you will find A is one flip-flop, where TCLKQ is 9 nanosecond. It has its own setup time 2 nanosecond, 1 nanosecond. Then B is also having few timing parameters. And there is a combinational design TPD which is 4 nanosecond. And lastly, you are having a C flip-flop with its own timing parameter. Then the data, whatever you are giving at input, it will appear at the output of the C flip-flop. Okay. So when these similar things happen, so what you have to do is you have to find out how many paths, timing paths are there. So one timing path is TAB, one is TAC, and one is TBC. Okay, so your clock period must be a value which must accommodate all these timing paths. That means whatever duration or delay happens during this timing path, data traveling from input to output within the any of these timing path, the maximum delay you have to take, and you have to divide that with 1 to get the maximum frequency of operation or clock period. Okay, so that's why you can see here TAB is equal to the TAB stands for TAB is the clock between both A and B. So TCLKQ is 9 nanosecond. Then you are coming to TB. So for that, you assume the data is stable at A, then it will pass through TCLKQ 9 nanosecond. Then setup time of the B, that is 2 nanosecond. So TAB path took around 11 nanosecond for the data traveling. Okay. Then the time traveling of data for TAC, time of traveling is, so in this case you will get TCLKQ A, then TPD of the second one, then T setup time of the third one, that is C. Okay. So TLKQA is 9 nanosecond, then TPD of the combinational design is 4 nanosecond, then setup time of the C flip-flop is 2 nanosecond. So total 15 nanosecond. Okay. Similarly for TBC, so TBC TCLKQ is 10 nanosecond, then TPD is 4 nanosecond for the combinational design, then 2 nanosecond for the setup of the C flip-flop. Okay, so total is 16 nanosecond. So you can find that TBC is having the largest path delay in these three timing paths what we have observing. Okay, so that's why the minimum clock period should be calculated from this value of 16 nanosecond. Okay, so T minimum is equal to 16 nanosecond, because if you will take, let's say, 11 nanosecond, then 15 and 16, in 11 nanosecond of the clock period, the clock will change. At that time, 15 nanosecond period path and 16 nanosecond period path doesn't or they didn't have changed, or they have not completed their operation, because to complete the data traveling and the operation in these two paths of TAC TBC, you require at least 15 nanosecond and 16 nanosecond. So that's why if you are making the minimum clock period as T 11 nanosecond, then these two paths data will become garbage because the data will be overridden. Okay. Similarly, that's why you are taking the maximum value of the delay here, that is 16 nanosecond, and that will be treated as, at least it will be the minimum clock period of the, see, maximum delay which is there 16 nanosecond, that will be the minimum clock period of your design. Okay, so T minimum is 16 nanosecond, and if you invert it, you can say that the maximum clock frequency of operation of this design is 62.5 megahertz. Okay, so this is one example. Another example we have taken, like circuit with, sometimes you will find circuit with both minimum and maximum delay. So actually what happens, like I told, when library vendors they give they also give circuit with minimum delay and maximum delay, and there are provisions in Verilog also. We have discussed this. Okay. So in that case, what you so here you see that's the same scenario, but in the clock path, we can say there is a data path traveling from flip flop one to in NOT gate, then to flip flop two, and there is a clock path means the synchronous connection of the flip flop one and flip flop two. There, in between that, there is a buffer. Okay, so in clock path also there is certain delay present. Okay, so this type of code when it happens, so this type of design when it comes, so what happens actually we need to see it. Okay, in order to find the minimum delay and maximum clock frequency. Okay, so can do is we have to find out as there are two delays associated with each wire. So what we have to do, we have to find the maximum delay by calculating the maximum value in the paths, and similarly minimum delay by calculating the by considering the all the minimum delays in that path. Okay, so you can see in data path, let's say in data path that is from CLK to Q, then inverter, then flip flop 2. Okay, so in that data path, what is my maximum delay? So we need to find out. Okay, you can see here fast is 2 nanosecond. After clock, there is a 2 nanosecond maximum delay. Then before your inverter, and then there is also flip-flop have a propagation delay which is 11 nanosecond. Then before inverter you have 2 nanosecond. Inverter has 9 nanosecond. Then before flip-flop 2 you are having 2 nanosecond. So the fast line written in data path maximum delay is 2 plus 11 plus 2 plus 9 plus 2 equal to 26 nanosecond. Okay. Similarly, what is the minimum delay in this data path is first one is 1, then 9, then 1, then 6 in the combinational logic, then 1 before your flip-flop 2.
Sir,
Huh.
sir, in maximum delay, why not setup time is considered, sir, for second flip-flop?
Okay, he has not considered here setup time. Let me see. So he has what he has done actually, he is actually see, just try to see here what you are calculating here when setup time is considered. Let me just give one answer. Like when TAS is considered, what we are doing? We are finding out the minimum time requires to the data to travel from input towards your output, right?
Yes, sir.
Or
Yes, sir.
T minimum you are finding out T minimum, right? So what happens here? Here actually he is finding out the delay in core. Okay, the T minimum he is finding out the in the second slide where he has considered the setup there.
Okay, sir.
Understood. So
Yes,
we'll come to that. Let us first here actually what we are doing, we are not finding out the clock now. We are just finding out what maximum delay in the data path and the clock path. Okay. So that we'll take that, we'll put to some formula, then set up, then you will find out the T minimum. Right. So that's why, so you can see in data path the minimum, what is happening here is here we don't have one delay, we are having two delay. So one is maximum, one is minimum. So in this case where you are having one delay, so you are just taking that delay, then putting setup, you are getting the T minimum of that particular timing path. Okay. So as here there are two delays, so you will be confused that which delay to consider. So what he is doing is he is finding out first what is the maximum delay and minimum delay in a corresponding timing path and clock path. Then they will see how to find out the T minimum in this entire circuit. Okay. So data path maximum delay is 26 nanosecond, and data path minimum delay is 18 nanosecond. Similarly, in the clock path, the maximum delay you can see here, first is 3 nanosecond, the below line, then buffer is 9 nanosecond, then 3 nanosecond. So that at least the data is available here, but means we are just finding out the delay. We are not considering setup, so we are not till now we are not calculating the T minimum clock. We are not calculating the minimum period of the clock. We are only calculating the path delays. Okay. So this is equal to 15 nanosecond in maximum delay of the clock path. Similarly, the minimum delay of the clock path is 2 nanosecond plus 5 nanosecond plus 2 nanosecond, which is 9 nanosecond. So now we have just reached up to the input of this flip-flop. So in order to find the clock or T minimum, no doubt we have to add the setup. But where to add, that is the point of discussion here, because we are having two types of delay, which is bit confusing. Like we are not having only one delay here. Okay, so now what he is telling, there may be a chance that we may have four different combinations of clock period here. So what, how to find out is, first you take maximum data path delay minus maximum clock path delay plus t setup. Okay, so first maximum clock is 26, then maximum is 15. Okay, so he is subtracting 26 minus 15 plus 4, and now in this notation, the T minimum 1 is 15 nanosecond. Okay, then second, he is taking minimum data path delay minus maximum clock delay, then T setup, which is 7 nanosecond. In the third, maximum data path delay minus minimum clock path delay plus T setup, which is 21 nanosecond. Then the final one is minimum data path delay minus minimum clock path delay plus T setup, which is equal to 11 nanosecond. Okay. So as the most of the delays are maxi data path delays are higher than the clock path delay, so he has subtracted clock path delays from data path delays, and they have taken all possible combinations like maximum data path, minimum data path, maximum clock path, minimum clock path. Then with that, they have added the setup according to our old formula. Then they have seen that in the third T3 or third clock period, where we are taking maximum data path delay and we are considering minimum clock path delay, with that setup time, we are getting a value of 21 nanosecond. Okay, so this at least to uh, complete all the operation in this particular design, our minimum clock period must be equal to clock period T3, which is maximum data path delay minus minimum clock path delay plus T setup. So 26 minus 9 plus 4 is 21 nanosecond. So now from here, you have to find out the maximum clock frequency by inverting it. Okay, so just remember there are few formulas coming out of this discussion, from these discussions. So those things you remember. If you know all these things, so somebody is asking, you can directly give the formula instead of analyzing the things. So first formula we saw is that maximum clock frequency is equal to 1 by minimum clock period, where minimum clock period is equal to propagation delay of flip-flop A plus propagation delay of combinational design and the setup time of the flip-flop B. Okay. Then second one is, if there are two timing paths, then minimum clock period is equal to maximum data path delay minus minimum clock path delay plus T setup of the second flip-flop. Okay, out of that you invert it, you will get the maximum clock frequency. Okay, so this is to see that the setup time plays a very important role while deciding the clock period of a design, or you can say maximum clock frequency of a design. Okay, so please remember these two formulas. Depending upon design configuration, it may change, but at least this type of formula will get minimum. This formula will be there. Okay. Then now we'll get back to our main topic, which is actually finding out the setup violation and hold violation. And we are discussing about static timing analysis. So we have yesterday discussed that this is bit different from your dynamic timing analysis. So dynamic timing analysis checks for correctness of the functionality. Okay, but static timing analysis doesn't check about the correctness of the or functionality of the design. It just divide entire design into timing paths, so paths between flops, and those flops will be individually calculated for the setup and hold violation. Okay, so that is what static timing analysis does. But in reality, there are complex designs. So we are seeing very complex designs. So no doubt there will be many flops. So what happens actually, we use sophisticated tools, or you can say advanced tools like CAD tools like Synopsys Prime Time. In Cadence, I think they are having encountered timing or some tool is there, because prime time is so famous. So we generally use that one. So but Cadence do have, mental graphics do have a solution for their from their company. Okay, and most of the structure input output of these solutions are same. Like all these in algorithm tools are same. Okay, they will take the same timing characteristic as a design constraint, your RTL level, get level netlist after synthesis, and vendor specific library and add its parameters. Okay, and they will find out the setup violation in each timing path. Okay, so tool can do it for you very easily. So very optimized tools are being designed, and after that you have to observe that in each timing path what is your required time and what is your arrival time. So we have discussed last class the required time and arrival time. So in that we have seen that there is a term comes that is called slack. Slack is equal to required time by arrival time. So required time is mostly calculated by the your clock period minus your setup time. Okay, and arrival time is the actual time which where when the data reached. So there may be a chance that data may reach before your required time. So at that time your slack is positive and you don't have any violation. Okay, and if arrival time of the data is more than the required time, then slack is negative and you have certain violations. Okay, so tools will just give you the result. Prime time tools will give you the result of the slack. Okay, so what is the slack? So if you see slack is positive, then there is no violation. If you see slack is negative, then there are certain violations exist. Okay, so you can say setup violation exists. Sometimes in order to correct setup violation, you may or in order to correct either of the violation, you may able to violate the other one. Like let's say there is a setup violation is there, you are rectifying it, and you will see that after rectifying it by adding certain delay so that it will reach at the actual point, or reducing delay or sometimes, so you will see that hold will be violated. And sometimes you see when you are uh, trying to decrease hold violation or nullify the hold violation, setup will be violated. So those examples will now see. Okay, so for those examples our basis circuit is same. So we are assuming that in your generalized circuit, any complex circuit, the timing path will be like this. There will be a combinational path between two flip-flops. Okay, and we also observed last class the hold is calculated between at the same edge of your clock pulse, but setup is calculated at the next edge of your clock pulse. So which you can see in the lower part of this diagram. Okay. Now we'll go through 3 to 4 examples. So how to do the setup and hold violations, right? So first example is our example one. So we have taken specification of the flip-flop circuit. So these all examples and all the slides I have taken from VLSI experts slide, because I feel that in that many things given very properly. So so frankly speaking, I am teaching this subject from 2011. So initial days, we started teaching VHDL, then followed by we migrate to Verilog. Then I used to teach both. In between, then I stopped teaching VHDL because if you know Verilog, you some moment of time you can learn VHDL on your own. And I told many ASIC design tools they supports Verilog directly instead of VHDL as they are gate level native, so we thought to migrate there. But if you are a FPGA designer, then in my personal opinion, no SDL matters for FPGA designer because today's FPGA nowadays it works on Python also. Okay, you can write a Python code. Pink Jet2 board is there by Xilinx. So where P, Y, and Q. So where they write the code in Python and they put in FPGA. Okay. So and also MATLAB code you can write and put in FPGA. You can write some sort of C code and you can put in FPGA. So if it is FPGA, so you know how FPGA differs from ASIC. So when it is FPGA, your main requirement is that you have to do the design and you have to meet the your design requirement. Means your specification is meeting or not, you are checking on the FPGA without going for a ASIC fabrication, which required at least 3 months of duration along with the time, along with the money, okay, investment. So that's why in FPGA, as the market is going fast, and sometimes in order to learn do this machine learning and all, so you require Python. Python is more better than MATLAB. People are telling. So in that's why Xilinx has adopted Python language so that it can be converted to SDL by tool. So you have to write the code in Python. It will be converted to SDL, maybe VHDL or maybe Verilog. Then that code will be ported in the FPGA. So if it is FPGA, then you learn any tools, any SDL, it doesn't matter. But sometimes in ASIC point of view, cheap point of view, if you are learning Verilog, it is easy because if you know Verilog, you can learn system Verilog, which is the verification language mostly required to in the jobs like verification engineer in the market or in the industry. Okay, so most of the jobs I told in the industry are based on verification engineers. So for one engineer, they require at least 3 to 4 verification engineer. So who will sit to find out the bug in the design, and they will tell designer engineer that your design is not correct. Okay, in the way of finding the bug, they will save money of their company. Okay, because a faulty IC and corresponding a system in market will if it is going, then the company will lose its market value. Okay, and the product time to market will reduce. Okay, it will. Oh, sorry, time to market will increase. Though even though you will launch in the market without proper testing and all, then in market it may become fault and it may not work. Okay, so that's why they may lose market. So verification jobs are more. So that's why they require this system Verilog, which you can understand on your own, a bit difficult than Verilog, but you can try and learn on your own, provided if you know it Verilog. So it will become easy. Okay. So that's why this is what is required. So that's why if it is coming to our topic, if it is ASIC design, so at that time, mostly this static timing analysis will happen. There is this also there in FPGA design also, but what we are discussing here, it is from the ASIC point of view. Okay, so in our example one, the specification of the flip-flops are given. So you require setup time 2 nanosecond, hold 1 nanosecond, clock period 10 nanosecond. We are assuming a ideal flip-flop. So TCLK2Q, this is the delay of the propagation delay of the flip-flop is 0. And there is net delay is also ideal, that is 0. That net delay are the delays in the nets. Okay. So from flip-flop to combinational logic, there is a net, and again combinational logic to flip-flop, there is a net, next flip-flop. So those net delays are also we have taken as zero. So if there is any zero, it will be add up while finding out the final clock frequency or doing the setup violation. Okay. Now the combinational logic block in between your two flip-flops has a delay of 0.5 nanosecond. So now it's on you. I am leaving. You just try to do it and let me know whether it is having setup violation or not. I will discuss, no doubt. You take 2 minutes, trigger your mind, and just let me know. It is in a bold letter. It is showing there is no setup violation in particular specification of the flip-flop circuit. So, are you agree to this? Are you agreeing? All of you agreeing to this? Just once you just give some time, because if I will keep on telling only you will listen, that is okay, but if you will trigger your mind you will learn more. Just take 2 minutes and let me know whether this circuit has no has setup violation or not. Though it is showing in bold that it is having setup violation, also it is not having setup violation, but it is having hold violation. So now you will see how to just minimize these hold violations. So setup is checked in the next clock edge and hold is checked in the current clock edge. Are you listening to me?
Yes, sir.
Okay, just read out few lines in the top. See, because the fast code, na, so if you will trigger your mind, then second will be easy, and no doubt second will be tough than this. So that's why you should go in that way. And we don't have any blackboard concept here, so I can't write. Okay, I am reading one by one, though I can understand, make you understand in a one line, but better let us go with the flow. And it took time, but you will understand in a better way. So let us discuss the flow of the data from FF1 to FF2. So just see the diagram once. Okay. So data is going to launch from FF1 at positive clock edge at 0 nanosecond, and it will reach at FF2 after zero point 0.5 nanosecond, because we have taken the propagation delay of FF1 as 0 and combination logic delay as zero point 0.5 nanosecond. Okay, so it will reach at the error point at the input at after zero point 0.5 nanosecond. Okay, so data is going to launch from FF1 at positive clock edge at 0 nanosecond, and it will reach at FF2 after zero point 0.5 nanosecond. Okay, so that is the delay incurred, which is called as combination logic delay only. Okay, only this delay is there, no delay in between. Okay, now this data is going to capture at FF2. So this data is going to capture at FF2 when it will be captured at the positive edge of your 10 nanosecond, not at 0 nanosecond. The data is launched at the 10 nanosecond of the clock period, which is next clock edge. At that time, it will be captured. So we have to see here that whether the data is reached well before the setup time, keeping time clock is at 10 nanosecond. So if it is reached well before, then there is no setup violation. If it is reaching after that setup time, then it is setup violation. Okay. So as for the setup definition, data should be stable 2 nanosecond. So setup time is 2 nanosecond. So data should be stable 2 nanosecond. That is setup time of the flip-flop 2 at FF2 before the positive edge of your clock, that is 10 nanosecond. That means 10 nanosecond minus 2 nanosecond. So data must be available before 8 nanosecond. or at 8 nanosecond. Okay, then only there is no setup time. So now you see our data is available after zero point 0.5 nanosecond of the zero time unit. So that means from 10 time units, the data is available before 9.5 nanosecond. That is 10 nanos with respect to zero, the initiation or launching age of your data, zero time unit. Okay, so with respect to zero time unit, data is available somewhere at zero point 0.5 nanosecond here. Okay, but with respect to 10, if you will see 10 minus 0.5, so data is available 9.5 nanosecond, which is much before of the 8 nanosecond. Are you getting? So setup evaluation is there or not? You tell me.
Or
No, sir.
not there, sir. There is positive
Okay,
slack
so
of 7.5 nanosecond.
No, sir.
okay, so slack is your required time here is 8 nanosecond, right? Arrival time is zero point 0.5 nanosecond. So what he is telling, 8 minus zero point 0.5, your slack is positive, that is 7.5 nanosecond. So he has given another good concept. So now there is no setup violation. Okay, so now we have to see setup violation is not there when we consider the data capturing at the next stage of your clock pulse. Okay, now this data is present at 8 nanosecond, so it will be last at the 10 nanosecond pulses of your clock pulse. Then this data must be hold up to what period? That is 10
One
plus 1 nanosecond. That is your hold period, right? So 10 plus 1, so data must be stable from 8 to 11 nanosecond. Okay, so at 10 nanosecond, what will happen? The second data will be launched at the 0 nanosecond period. Understood my point? So when you are at 0 nanosecond, the first data is launched here. So if I am moving my arrow in the screen, is it visible to you or no?
Yes, sir.
Yeah. Huh? Huh?
Yes, sir.
So
Arrow
it is.
moving is visible, right?
Yes,
Yes, sir. Visible.
Okay, so when 0 nanosecond is there, data is launched, it is captured in here. So setup time we have seen here, which is in the next stage of your clock pulse, and it is no setup violation. So my data is available at 8 nanosecond. It should be hold after 10, that is 1 nanosecond. My hold is 1. So from 8 to 11, there should not be any data changing. Understood? So what will happen when your data is here, means 10 nanosecond, you are capturing the data. At the same time, there may be a chance one data will enter in the flip-flop 1. Okay, now we have to see that when we are at 10 or 11 nanosecond, if flip-flop 1 is taking another input of data, whether it is reaching at FF2 beyond the whole time or before it. So if it is reaching before it, then there will be a garbage of data. Data will be mixed. Okay, so we have to see that this data must reach after the whole period. That is after 11 nanosecond. Okay, but what happens here? The second set of data is going to update and override the first set of data because it reach only after 10 plus zero point 0.5 nanosecond, because your combinational design, see, fast flip-flop at 10 nanosecond launch a another data which took zero point 0.5 nanosecond here to reach here. Okay, so 10 plus zero point 0.5 is 10.5 nanosecond. So at 10.5 nanosecond, we have another set of data. But the fast data which has launched at 0 nanosecond, that was actually, that should be stable up to 11 nanosecond. Okay, so we should get this second data after 11 nanosecond. Let's say 11.5 or so. Okay, then only there will be no hold violation. Okay, so reading out for your better understanding again. So at the flip-flop 1, second set of data is going to launch at t equal to 10 nanosecond. And okay, so you remember this line, at flip-flop 1, second set of data is going to launch at t equal to 10 nanosecond. and it will reach the FF2 in another 0.5 nanosecond, that is t equal to 10.5 nanosecond. This second set of data is going to update or override the first set of data. As per the whole definition, data should be stable till 1 nanosecond, that is the whole time of the FF2 at flip-flop 2 after the clock edge of 10 nanosecond, t equal to 10 nanosecond. Okay, so in the above case, first set of data is going to override by second set of data at 10.5 nanosecond, means just after the 0.5 nanosecond of the positive edge of your flip-flop 2. This means it is not satisfying the hold condition and there is a hold violation. Are you getting? So now you let me know what I should do so that there will be no hold violation here. It's a very simple thing. Please tell me.
Combination
Also,
logic
Increase combination delay,
stability
sir.
not 1 nanosecond.
so it is written in the bottom also. To fix this hold violation, we have to increase the delay of the data path so that the second set of data should not reach before 11 nanosecond. Okay, so 10 nanosecond, that 0.5 nanosecond must be increased to 1 nanosecond. Okay, so that means the minimum delay of the combinational logic path should be 1 nanosecond for no hold violation. Okay, so I think all of you got this. So now we'll go to next slide. So now here we have to also summarize something, like you are telling that I will increase the delay of the combinational path. It has to be minimum of 1 nanosecond. Okay. So somebody will tell, sir, why 1 nanosecond? I will increase 2 nanoseconds. Somebody will take 3 nanoseconds. Somebody will take 5 nanoseconds. So we should have a limit to this. You can't unnecessarily keep on increasing. Okay. Because if you increase, then it may affect the setup violation. Okay. So now in this slide, we'll summarize, is there any generalized formula to see to observe a violation free circuit? Okay, so let us see here. So to fix this hold violation, we have to increase the delay of the data path so that the second set of data should not reach before 11 nanosecond. So that means the minimum delay of the combinational logic path should be 1 nanosecond for no hold violation, right? So in order to fix the hold violation, you can increase the delay of the data path by any method. So there are various methods given how to reduce the hold violation and setup violation towards the end of these slides. So one of the method is that you can put another buffer here and the delay will increase. Okay. Buffer with the 1 nanosecond or 0.5 nanosecond one buffer you can put. So it will increase the delay, right? But this buffer will not change the functionality of the design, but it will just help you to maintain the timing. Okay, so similarly other methods are given towards the end of the slide so that you can go through. Okay, then it does not mean that you can increase the delay by any value. So you can't increase the delay by any value, it will be a problem for you. Let us assume that you have increased the delay of the combinational path by adding extra buffer with a delay of 8.5 nanosecond. Okay, so we have seen that 1 nanosecond is the delay minimum required for combinational design for a whole for a free of hold violation in this particular specification of the design. So now let us see that we have changed the combinational delay. It was 0.5 nanosecond before, we have increased by 8.5 nanosecond, now it becomes 9 nanosecond. So the next specification of the circuit is given where only changes happen is combinational logic delay is 9 nanosecond. Okay. Now let us see what happens to setup violation. So if I am taking 9 nanosecond, so as it is coming after 1 nanosecond, so obviously there will be no hold violation, right? But there may be a chance that setup violation may occur. Okay. So that will conclude. As for the setup definition, data should be stable 2 nanosecond, that is setup time of the FF2 before the clock edge of the FF2, which is at 10 nanosecond. Okay. So with the updated specification, data will be stable at t equal to 9 nanosecond. Are you getting my point? If you'll go back again, find out, iterate your design. Initially, the data launched at 0 nanosecond, and after 0.5 nanosecond it was present, which is much like your slack is positive, which is much before your 8 nanosecond is the required time. Okay. If you are increasing the delay to 9 nanoseconds, so after 9 nanosecond it will reach, so your slack will become -1. Okay, so it shows that there is a setup violation. Okay, so since data path delay is more than 1 nanosecond, there is no hold violation, but you have still setup violation. So it puts a limit that you can't unnecessarily increase the combinational logic delay, right? Okay, so it means that 8 nanosecond. So what is the maximum delay? If minimum delay is 1 nanosecond, what will be the maximum delay of the combinational logic block? So that is equal to 10 minus 2, 8 nanosecond. So at 8 nanosecond, which is my required time, by that time the data must reach or data must arrives. Okay, so it means that 8 nanosecond is the maximum value of the delay of the combinational logic path for no setup violation. Okay, so if I will generalize, can we say this? For no hold and setup violation, the delay of the path should be in between 1 nanosecond and 8 nanosecond. So see, 1 nanosecond is the hold value, 8 nanosecond is the 10 nanosecond minus 2, which is clock period minus setup time in this design. Okay, so for violation circuit, in other way we can say minimum delay of combinational path must be greater than the hold time of the capture flip-flop. So it may be equal or it may be greater than 1 nanosecond. Okay, provided your maximum delay of this combinational path must be less than clock period minus setup time, so that you will have no hold and setup violation in the design. Are you getting, all of you, or any doubt? So we have generalized here, minimum delay of combinational path is greater than or equal to hold time of the capture flip-flop, and maximum delay of the combinational path is less than the clock period minus setup time of the capture flip-flop. Okay, you can see 10 nanosecond minus 2 is 8 nanosecond, which is the maximum delay, and hold is minimum 1 nanosecond. So it depends, the minimum delay depends on the hold, and maximum delay depends upon the hold and the clock period. Okay, so there are few generalized things I am telling you, please note it down. Then going to second example, there are two more examples are there. So we'll discuss, then we'll end up. So in the second example, what happens? Your setup time increased to 6 nanosecond and hold time increased to 5 nanosecond. Clock period is same 10 nanosecond, and combinational logic delay is 0.5 nanosecond, same. So you see whether setup violation is there or hold violation is there. So in earlier code, there was no setup violation, but hold violation. If you are increasing, then setup was coming. So now you see what happens. So here your setup is 6. So that means after 10 minus 6. So at 4 nanosecond, you must have the data arrived. Okay. But you will see as the combinational delay is 0.5 nanosecond. So data launched at 0 nanosecond has reached after 0.5 nanosecond before your 10 nanosecond of your clock is triggered. Okay, or before triggering of the second clock is, which is at 10 nanosecond. Okay, so that's why in bold you can see there is no setup violation, slack is positive. right? Now you see whether hold violation is there or not. You just see and let me know. So at 10 nanosecond, your hold is 5. So data must be stable up to 15 nanosecond. But if at 10 nanosecond the fast launching flip-flop launch a data, it will reach after 10.5. Okay, so that shows that the fast set of data which has launched in the 0 nanosecond period or time interval, that must be stable up to 15 nanosecond, but second set of data is launched at 10 nanosecond from the fast flip-flop and it is arriving at 10.5 nanosecond. So that's why it means that just after zero point 0.5 nanosecond of FF2 it arrives, it means that there is a hold violation. Okay, so now what to do in order to reduce the hold violation? What I need to do? Tell me.
Increase the combinational logic delay.
So increase the combinational logic delay by 5 nanosecond, right? So minimum 5 nanoseconds. So now it must be 10 plus 5 equal to 15 nanosecond. In that case, what is happening? Hold violation will become 0. So there will be no hold violation. Okay. But at the same time, you check whether is there any setup violation happening or not.
Yes, sir.
Why it is happening?
Slack is -1, sir. Negative.
-1. Okay, because your 10 nanosecond is there. If you are taking your combination logic delay as 5, then the data launching is reaching after how many period? Means 6 nanosecond. So it is reaching after 5 nanosecond. But we required it at like 10 minus 6 at 4 nanoseconds. So slack is your -1. Okay. So what will happen? There will be an setup violation. Okay. So how to fix it? So if you are in this case, if you are going to you have to nullify the whole violation, then setup violation is coming. Okay, and if you see, you can't do this in a general way because in this scenario we can't fix the setup and hold violation at the same time by adjusting the delay in the combination logic. Because are you getting my point? Because the setup violation as it is 5 nanosecond and the setup is 6, so you have to have a 5 nanosecond minimum in order to reduce the hold. Okay, in the previous case, what happens? Your delay was just 1 nanosecond, which is setup was is around 10 minus to 8 nanosecond. So you are having a buffer of 7 nanosecond. Okay, but here you don't have any buffer period. I am telling you buffer means buffer period. Because before 10 nanosecond minus 6, so at 4 nanosecond the data must be stable. But the combination logic required inherent delay of 5 nanosecond. So there is not possible that your data must reach before 5 nanosecond in order to avoid the hold violation. But if you are avoiding hold violation, then setup violation is occurring. Okay, so this is a condition or a situation when you can't adjust both at a time by only varying the delay in the combination logic. Are you getting? So what to do here? So the thing you need to do here is we have to fix the clock frequency, because within your clock period it is not possible that you can adjust the combinational logic block delay and fix both the setup and hold violation. So that's why it is written. Now the point is how to fix these violations. Actually, this is a non-fixable issue until you just change the clock frequency or replace the flip-flop with less setup and hold value. because there may be a chance in this scenario you may do two things. You can change the flip-flop with less setup and hold value, but there may be a chance you can't do it because your design required maybe this flip-flop with that setup time. Okay, so in that case what you have to do is you have to increase your clock period. Okay, so so what you need to do is you have to find out the minimum delay which is greater than equal to 5 nanosecond for the no hold violation, and your setup is must reach at 4 nanosecond. So that's why somewhere we are not able to get it. Okay, we are not able to breach this. So how to find out this? You have to find out this by increasing 1 nanosecond extra clock period. That means there is a setup violation or there is a slack of 1 nanosecond, right? Okay, so you have to take 10 nanosecond clock period plus add 1 nanosecond extra, then that slack will be adjusted. So now my new clock period is 11 nanosecond. So you see here. So whenever this type of question is given to you, first you cross check whether your setup and hold time when it adds up, whether it is equal to or greater than clock period or not. Okay, see in example 1, your setup is 2, hold is 1. So 3, clock period is far away from 310 nanosecond. So here both can be fixable by varying the combination logic block or something like that. Okay, but in this case, when you are having 6 plus 5, it is 11 nanosecond, and which is actually setup and hold itself becomes more than clock period. So sometimes you may come or you may encounter a non-fixable violation here. Okay, so another conclusion from here is for violation free circuit, your clock period must be greater than equal to setup time plus hold time. Okay, and you know this minimum delay of combinational paths must be greater than the hold time of capture flip-flop, and maximum delay of combinational path is less than the clock period minus setup time of capture flip-flop. Okay, and now we conclude. Summarize, clock period must be greater than equal to setup time plus hold time. Okay, so these are the three you can say generalized formula or summary you need to remember in order to, so you can directly see if setup and hold are more than clock, then you can directly say that this is the solution is you increase the clock. Okay, so now next example. So setup is 3, hold is 2, clock is 10, so which is less. Now here we are taking a condition like combinational logic delay is 5 nanosecond, and here the constant is it cannot be further reduced. So you have to take 5 nanosecond minimum. You can verify the setup and hold violation. Okay, so what he is doing here, he is putting directly the this summary. So clock period for this condition is satisfied because setup time hold time is 5 nanosecond, which is much less than the 10 nanosecond clock period. So condition for clock period is satisfying. The next condition is your minimum delay and hold condition conditional. So it also satisfied because your minimum delay is 5 nanosecond, which is greater than your hold time. So it means there is no hold violation. The third one is about maximum delay and setup condition. So we have to check whether the combinational delay, which is maximum, is 5 nanosecond, whether it is less than your clock period 10 nanosecond minus 3 nanosecond. So yes, it is 5 nanosecond is less than 7 nanosecond. So there is no setup violation. Okay. So if you will put all these conditions, you can say that uh, this circuit is a design which is free from all the violation, right? So you can go to summarize this. So in exam, if I am asking, please write the, you can summarize this, but please write the whatever discussion, because that will tell that you have understand in a better way. But in interview point of view, you can directly take this summary and you can approach them. If they ask what is the reason, you can go back and tell those reasons. Okay, so this is done. Now going to, I think this is maybe last slides, and after that there are few theories that I will leave you to read. I'm not going to tell you here. Okay, so then I think it is last one, last example, where the setup new specification of the flip-flop circuit setup is 4 nanosecond, hold is 3 nanosecond, clock period is 10 nanosecond, delay is 0, net delay is 0. Combinational logic design he has increased to 8 nanosecond, and it is written you can't further reduce it. Now what the constant he is putting here, that your combinational logic delay must be 8 nanosecond. You should not reduce it in any way to meet the setup or hold valuation or nullify the setup or hold valuation. Okay. So again, he has checked for the clock period. He has checked 4 plus 3 nanosecond setup for plus hold, which is less than clock period. So it's satisfied this condition. Then about minimum delay of combinational logic, he has checked minimum delay. Combinational delay is 8 nanosecond, which must be greater than the hold time. So 3 nanosecond. So it's fine. So no hold violation. So it's satisfied the whole condition. Then third is the setup condition, in which we have to observe the combinational delay maximum value, which should be less than the clock period 10 nanosecond minus the whole 4 nanosecond. So now you see 8 nanosecond is not less than 6 nanosecond. So here there is a slack negative issue is coming. So that's why there is a setup violation here. Okay. So setup violation here, but again your question wants that you should not reduce 8 nanosecond to less. So now how to approach all these questions, or how to approach these type of issues? Okay, so these types of issues can be approached by increasing the delay in the clock path. So delay in the T capture, that you can put a buffer T capture. Okay, you are seeing here. So you can increase the delay in the clock path, then only it is possible. Okay, so let us read out few points. So since we can't change this combinational delay and also setup time of for the flip flop, so we have to think something else. So we can't touch the data path. We can try it with the clock path. Okay. So flow of the data from FF1 to FF2 is like this. Let us assume that you have added one buffer of T capture delay in the clock path between the FF1 to FF2. So it is in the clock path. Okay, so delay you are increasing. So data is going to launch from FF1 at clock is 0 nanosecond, will reach after 8 nanosecond. Okay, after 8 nanosecond, that is combinational logic delay only, right? So this data is going to capture at FF2 at clock is at 10 nanosecond plus T capture because the delay added by the buffer. Okay, so as per the setup condition, data should be stable 4 nanosecond. So it is setup is 4 nanosecond. Okay, 4 nanosecond setup time of FF2 before the clock is at FF2. And in the above case, clock edge is now increased to T capture plus 10 nanosecond. Okay, so for no setup violation, 8 nanosecond combinational delay must be less than T capture plus 10 nanosecond minus 4 nanosecond, which is setup time. So 12 minus 10, which is less than T capture. So now T capture must be greater than 2 nanosecond. Are you getting? So if I am taking my T capture as 3 nanosecond, then my clock, which is 10 nanosecond, the period will increase to 13. Okay, and there will be no setup violation in this circuit. All of you got? Okay, so now there are few scenarios we have taken, and all the possible combination of scenarios we are taking and we are discussing. Now let us take the hold valuation. So what is happening here in summary? So this figure is a bit different where they have given this tea lunch. So don't see this. So what D has done, just forget about tea lunch in this figure. For our example, which we are discussing, maybe example 4. So as we can't reduce combinational logic part delay, so the only option is increase the clock delay. So when we are increasing the clock delay, what he is doing is he is finding out combinational maximum delay 8 nanosecond, which is fixed by less than of t capture plus the clock, then minus setup time. So from here he is concluding t capture must be greater than 2 nanosecond. Okay, so now t capture we are taking as 3 nanosecond to have a setup violation free circuit. Okay, so now check about the whole violation. At the FF1, second set of data is going to launch at 10 nanosecond. Okay, so and it will reach the FF2 in another 8 nanosecond, that is 18 nanosecond, right? So the second set of data is going to update and overwrite the first set of data present at FF2. So as for the whole violation, data should be stable till 3 nanosecond of the whole period at the clock edge of the FF2. So that is 10 nanosecond plus 3 nanosecond, where 3 nanosecond is the capture. So 13 nanosecond is now the entire time. Then data must remain stable for another whole violation, which is 3 nanosecond. So now data must be stable up to 16 nanosecond. Okay, so in the above case, the second set of data is going to override only after 18 nanosecond. Okay, so what we are doing is, as we have seen that T capture is 3 nanosecond for a setup violation free circuit, we are cross checking the hold whether it is affected or not. So we saw that 10 nanosecond clock, then 3 nanosecond T capture, then 3 nanosecond hold, which adds up to 16 nanosecond. But as the delay in the combinational circuit is 8 nanosecond, so data will reach the second launch data at flip-flop 1 will reach at flip-flop 2 after 18 nanosecond, which is much much after the 16 nanosecond, which is the holding period requirement of this circuit. Okay, so it means there is no hold violation. So are you getting? So these are all possible scenarios may happen. So that we discussed, and at least now you can able to answer at least 50 to 60% of questions if somebody is asking. And again, I will emphasize that you read it again and read the blog or read. There are lots of video courses available in the YouTube. You download everything. Any of you can download and you can share us. We will. I will also happy to read and learn. Your friends can also be happy to do that, or you individually download. Try to read it. Okay. Next semester, your Monday class will start, I think, but there may be a chance one will start, one may not start. So take another 1 2 day or take this weekend and try to wind up setup violation, or try to learn as much as possible about this thing. Because again, you will go to second year mode, then this first year thing will be on hold for some time till your exam will be coming, right? So now let us generalize the concept, then we'll conclude. So there may be a chance that there may be a buffer we may add in the tea lunch. So see, in the tea lunch, there is a green color. So there may be a buffer will be added. So this period will be tea lunch. So you can see clock FF1 is there. Then clock FF2 is increased because clock FF1 is now becoming 0 plus T lunch, and clock FF2 is starting at 0 plus T capture. Okay, so in order to, so now it's the final complete circuit where we are having lunch buffer delay and also capture buffer delay, and we have already discussed many possible combination about the combinational logic delays, etc. Okay, and setup and hold violation. So now to generalize this concept, because setup time is or new specification of the circuit is setup time is T, clock period is clock period. Okay, there is no delay. So if these delays are also coming, you have to consider this while finding out the setup and hold valuation. Okay. Then combinational logic delay is your TD. Launch delay is T launch, and T capture is the delay for the clock part. So now what he is telling is, as per the setup violation, your data should be stable T setup time before the clock edge of the FF2. Means data should reach at FF2 with a time period which is equal to clock period plus T capture minus T setup. Okay, because see, clock period was there, T capture is being added, and T setup has to be minus. So at that time data must arrive. Okay, so for no setup violation circuit, what you need to check, so like you are checking here, for no setup violation circuit, what you are checking? You are checking the combinational part delay TD, which is less than clock period plus setup time. Okay, sorry, minus setup time. So here you see combinational part delay is TD, but with that delay, T launch is also added. Okay, so T launch plus TD, which is less than clock period, again T capture is added minus T setup. Okay, so now new value of TD is less than equal to clock period plus T capture minus T launch minus T setup. So if you are having T launch and T capture in the circuit, then your violation free circuit for setup violation free circuit, this is the formula. Okay, so only we are adding T capture and T launch. Similarly, for no hold violation, the formula you can conclude like TD must be, it was before T greater than T hold, so now it must be greater than T capture minus T launch plus T hold. Okay, and your clock period must be always greater than setup time and hold time. Okay, so this is a generalized method where we have taken T capture, at the same time we have taken T launch delays, okay, into consideration. Okay, then what I can say is, so these, please you go through this again. I don't know if all of you get everything in a single instance or not. So you should go and write down this course in your exam, sorry, in your copy. You sit and write down everything and have your own summary so that you can directly answer questions, okay, in interviews if they are asking. And there are ways given here, 8 ways to fix setup time, and 2 ways till now you already discovered by how to increase or reducing the combinational logic clock or adding the delays in the clock path, etc. Okay, but even though they have given 8 ways to fix setup violation and 2 ways to fix hold violation, so I will not add any extra class to this semester. So you please go through it. If any doubt, I can clarify you over MS Team individually or in a group. Okay. And before summarizing, so the last thing we'll summarize here is, following points are recommended while fixing setup and hold violation. So make modification to data path only most of the time if it is possible, and you can change it. Adjusting register location or removing or adding buffers to the clock path will fix the violation. Means anyway you first try to change the data path. If it is not happening, then try to see the clock path. Also try to observe the entire duration of the clock, which must be equal to or greater than hold and setup time. Okay. First try to fix setup violation as much as possible. Then try and start fixing hold violation. In general, hold time will be fixed during backend. Generally what happens, setup time violation is checked in the front end. So I told in the VLSI design flow from where I started my class. So that is everything. See, if you are working in IC designing or doing research, maybe in this area, so you have to understand the VLSI design flow from its process, from its EDA tool perspective. So where, how it is happening? See, frankly speaking, I might have told in my first class when I started everything as a student in 2006, I took almost 1 year to understand the flow because there was very less faculty at that time in our department. Only Mahapatra sir was there. Under KK Mahapatra sir, under his guidance, we learned everything initially, and we used to go through SMDP project. We used to from ministry funding. I told ministry funding SMDP around 101 crore for each NIT and NITs and 1.2 or 5 crore for each IITs. So in the first phase, they have given all the tools and PC, printer, scanner, projector, everything. In the second phase, they have given only the tools. They told your institute must provide the printer. Okay. So funding sometimes varies depending uh, upon something. So that I don't want to mention here. So now our lab is funded by Ministry of Information Technology, MIT. Your MTech is funded by them. So entire VLSI MTech running in India is funded by them initially, or it is a start from them only. It start around in 2004 or 5. Beyond that, SMDP 1 was there. The program name is Special Manpower Development Program 1. It runs up to 2005. So there, at that time, Linux was not there. There was an operating system called Sun Solaris. So they gave 3 PC. In that, Sun Solaris is installed. Synopsys Cadence was installed, and Synopsys was that time very much high in Cadence when it was heavily used. So till today, we are having those PCs in our lab because we need to show uh, mighty stocks. Okay, so those are there somewhere in some closed cell or closed room. After that, 2005, they again 2006 the project pipe approved. 2006 the project came. So in that I joined as a project staff. In that I continued my MTech here. So under SAR's guidance, at that time only SAR was the only faculty in VLSI. Then slowly Acharya sir joined, then I joined, then others, Sarkar sir, Atin sir, everybody joined now. Then at that time we took 1 hour. There was a person called, there are 3 persons with me, so now they are not here. So we 4 sit and learn the things, and we found initially my BTech is electrical, so I came here first time. So anyone from electrical, electronics, computer science, they can read VLSI or embedded. It's not a big deal. But initially, I took around 3 months to understand the keywords in this area. Then 1 year to understand the flow. Then I came to know why we are doing the things. And if you will do the same thing in tool, then you will understand. Okay. Now what we are teaching to you, we are trying to honestly giving back the things we learn on our own or by attending training in SMDP in sports or mighty in IITs or somewhere. So that's why after that I took around 1 hour within a 4-person group under SAR to understand the flow, because in 1 hour we are slowly working in the tool to understand what is happening where. Okay, so that's why VLSI design 2 is a very important means prospect. So you can see many faculties, many industry fellows, they will give their ideas in VLSI flow. So that you should acquire and you should gather knowledge from them. Okay, and in that flow, I told many times there is a front end and back end. Up to synthesis, it is front end flow. After synthesis, this physical placement and routing or layout are part of your back end. So mostly in front end, in prime time, they see both setup and hold time. But mostly in front end, they check the setup time. Okay, so whole time they keep to last, because after place and route they have to check that what are the capacitance based delays are occurring due to net delays. That's why if you will do PNR and all place and routing using SOC encounter or IC compiler of Synosys, they check a whole time violation once your layout is done. Okay, so that is a tool perspective I am telling. So that's why it is written here. In general, hold time will be fixed during the backend, during PNR, place and routing while building clock tree. So generally a clock tree is built in the place and route phase. Okay, so when clock tree is built, then hold violation is checked. So if you are a front-end designer, concentrate on the fixing of the setup time violation rather than hold time violation. But you remember, both violation has to be fixed. Okay. Now the concluding word is fix all the hold violation if you have to choose between setup and hold. Okay, what I told, the same thing. Okay, if you have to choose between setup and hold, fix the hold violation. Okay. So now if a chip is done with some setup violation. So these lines may be contradicting, but if you work upon tools, you will understand in a better way. Okay. So if a chip is done with some setup violation, it can work by reducing the frequency. See, so how you are deciding the frequency? By adding the setup time. So if you are not giving the setup time, then your frequency of operation will be reduced by the setup period. That is around 2 nanosecond, 3 nanosecond, or maximum 6 nanosecond, let's say. Okay. But if a chip is done with hold violation, means if you are doing with hold violation, then we have to just dump the chip, because the data will become garbage. The data is overridden. So whatever input you are giving, it is never the same input, or desired input never reach the desired at the output. Understood? So if a chip is done with some setup violation, I am not telling entire setup violation, it will not work. Some setup violation, it can work by reducing the frequency. But if a chip is done with a hold violation or with hold violation, we have to just dump the chip, because the data will be override and it will become garbage. Okay, so this is all about my class in this semester. Hope you have learned something. And I always advise you learn on your own, try to give to others, so that it will be, once you are giving others, it will be in your mind, and you, once you are clarifying their doubts, you will become more better experienced. Okay, and try to gather more knowledge. Whatever I taught you, you share with me, I will happy to learn, because I am feeling personally I am teaching the same thing, and my learning phase, somehow it is reduced due to many admin work in college or purchase work. Actually, I can't able to learn myself, but sometimes if people are learning something new, please share with me. I will take some free time in weekend and I will try to learn it. Okay. And if I am learning something, I will also revert back to you, because this group will be there here. So I can post here some new things. If I am learning, you can learn in next 1 year, or if you are there here. So these things are ideal saying, I am saying. So you do on your side, I will try to do on my side. But again, due to busy schedule, you will be busy in your coursework, I will be busy in many things. So it may happen or may not, but we have to plan accordingly if you want to learn many things. Okay. And you personally try to learn. See, my last or first advice and last advice always to all these MTech students uh, is something like, so this is this we should acknowledge him. Okay, this block. So it's something like, please utilize your time perfectly here. Stop recording.